Right. There we go. I hope you can see that first slide. So this talk is on photo dissociation region, or PDR, theory and models. I'll also talk a little bit about H2 region diagnostics that can provide boundary conditions for PDR models. And then after this talk, Mark Pound will be talking about some of our online analysis tools that use these models to get some physical conditions from your observations. So this is a talk that I like to call Stars, Cars, and PDRs. And I'll start off with an introduction to PDRs, just a brief introduction. What are they? Where are they found? And some general characteristics. Then we'll look at the structure and chemistry of PDRs, the dominant heating and cooling processes, where the cooling lines are formed, and what you can learn from them. And then we'll look at PDR models in comparison to observations and finish off with some caveats, some things to watch out for if your models don't quite work or if they need some adjustment. Okay, so you probably know by now a PDR is a photo dissociation region. A working definition is that a PDR is a gas phase in which the ultraviolet radiation plays a role in the heating or the chemistry. The range in UV energies I'm talking about is between 6 EVs and 13.6 EVs. The upper end here is the ionization edge of hydrogen. So these are hydrogen neutral regions. The UV field is usually measured in units of the interstellar field. So G0 of 1 is an interstellar field, and G0 usually is intended to mean a Hobbing field. There are other measures of interstellar fields, though. There's the Drain field and the Mathis field, but they are all within about a factor of 2 of each other. So a Hobbing field has an energy flux of 1.6 times 10 to the minus 3 ergs per centimeter squared per second, and a photon flux of about 10 to the 8th photons per centimeter squared per second. And we normally find fields between G0 of 1 for the interstellar field, or G0 of 10 to the 5, which is the field directly behind the trapezium stars in the Orion Nebula. So where do we find these things? One place is where O and B stars shine on nearby molecular clouds. So we have an H2 region surrounding the O and B stars, and the UV radiation that escapes from the H2 region illuminates this nearby cloud, and that creates a PDR. Sometimes this is called a classic PDR. At the very surface, we have C plus H1 gas. A little bit deeper in, we have C plus H2 gas. So this is the so-called dark molecular gas because it doesn't emit very strongly in CO. And then we have the rest of the molecular cloud. Now, using this definition, the PDR can extend almost entirely across this molecular cloud. So most of this molecular gas is also in the PDR. We also have PDRs in the diffuse gas. This is a cold atomic gas cloud of temperature about 80 degrees. And here is a warm atomic hydrogen cloud of temperature of 8,000 degrees. So this is the CNM and this is the WNM. And these clouds are also illuminated by the ultraviolet radiation from the interstellar field. So these are also PDRs, although here the UV fields and the densities and column densities are much smaller than you'd find in these classic PDRs. If you look at the ISM as a whole, most of the non-stellar baryons and galaxies are in PDRs. You also find PDRs in early stages of star formation, where this protostar is still enveloped in its molecular gas. You find PDRs in protostellar disks and outflows, but here the densities and column densities are much higher than you'd find in the classic PDRs. And you find PDRs in this late stages of evolution where due to mass loss and stellar winds, there's these shells of material that are also illuminated, and those also produce PDRs. So here's a schematic of a PDR as a function of AV into the cloud. You've already seen this a few times, but I'm going to go over a few more details here. So on the outer edge, you have a source of ultraviolet radiation or ionizing radiation. And before you even get to the PDR, there's an H2 region of H plus gas, and temperature is about 7,000 to 10,000 degrees. You see recombination lines from hydrogen and helium. There's fine structure lines of metals that are excited by collisions with electrons. And there's a bunch of optical recombination lines from metals. Then deeper into the cloud, this is where the neutral gas starts. There's hydrogen and neutral helium. There's ionized carbon and neutral oxygen. The heating is mainly by grain photoelectric heating, and that's mainly from PAS. And that photoelectric heating is balanced by cooling by C plus and O1 fine structure lines. There's also fine structure line emission from heavier elements like silicon and iron. Here, these are excited by collisions with atomic hydrogen and not electrons. There's dust continuum emission, and then there's the PA emission. So that balance between heating and cooling typically gives temperatures between 100 and 1,000 degrees. You can get lower temperatures or higher temperatures depending on the ratio of the UV field over density. Then deeper into the cloud, the UV is diminished due to dust opacity. H2 starts to form on dust grains, but it's no longer dissociated. So you have a transition between atomic to molecular hydrogen. C plus can combine with electrons to form neutral carbon. The heating is still by grain photoelectric heating and balanced by C plus and O1 line cooling. You also start to see the C1 fine structure lines, and you also see vibrational and rotational excitation of H2 and other molecules. Now, this transition between H and H2 is called the dissociation front, and the transition between H plus and H is called the ionization front. And these transitions are a function of the UV field over the density. So for high G0 over N, these can be pushed deeper into the cloud. For low G0 over N, so you have a high density clump, these transitions move closer to the cloud surface. And in fact, they can also almost align. They can almost be on top of each other. Then deeper in still, you form CO, and ice forms on dust grains. You see the high JCO lines. You can also see the low JCO lines deeper in. This is mainly heated by cosmic rays, but can also be heated by the infrared radiation that's produced at the surface and then penetrates deeper into the cloud. So PAS, these polycyclic aromatic hydrocarbons, play an important role in PDRs. They can dominate the photoelectric heating, they can govern the electron fraction, and they might be sites of H2 formation. One of the early papers which made this link between this broad infrared emission and PAS is this paper, Polycyclic Aromatic Hydrocarbons and the Unidentified Infrared Emission Bands Auto-Exhaust Along the Milky Way, in which they favorably compare this infrared broad emission seen in Orion with auto-exhaust. So PAS dominate the heating by converting stellar photons into heat via this grain photoelectric effect. And PAS have an infrared emission spectrum that looks like auto-exhaust, hence stars, cars, and PDRs. Although my collaborator Mark has mentioned that with the increasing use of electric vehicles, we might have to change this, maybe stars, cigars, and PDRs. This is an illustration showing the process of calculating a PDR model. So you start at the outer edge of a cloud and you step inward, and for every step, you need to iterate around these processes shown in blue. So for chemical balance, you write down all of the formation and destruction rates you can think of for all the atoms and molecules, and you find the abundances for which formation equals destruction. Then down here, you find the temperature for which heating equals cooling, and there needs to be some kind of radiation transfer calculation or transfer approximation so that you know the local radiation field and you know the local line emissivities. But then all of these processes in blue are connected by additional processes. So if you want to find the thermal balance, you need to know the abundances of all the species, but then the abundances depend on the reaction rates, which depend on the temperature. In this chemical balance box, if you want to know the photo rates, you need to know the local radiation field, but the local radiation field also depends on the line opacity and the abundances of species. So you have to iterate around for all of these processes until they're converged. And then once they're converged, you know the abundances, the gas temperature, and the volume emissivities, and the local radiation field. And then you move on to the next step into the code, and you do this all over again. And so you keep stepping through, and by the time you get to the edge of the cloud, then you know the emergent line intensities. Now, there are several groups that are working on the PDR codes. Lars also mentioned some of these. There's the UMD group, that's our group. We have built on the original Thielens and Hollenbach PDR code with many updates along the way. There's the Meudon code. There's a complete description given by Franck Lapetit, but then there's also many updates since then. There's the Cosma Tau code with a very complete description recently by Asenkopf et al. There's the Cloudy codes. The Cloudy code was originally an H2 region code, but they've also adopted it to do the neutral gas, the PDR gas as well. And there's the University College London or UCL PDR code. Now, some of these are for plane parallel geometry or 1D spherical geometry. The Cosma Tau code has the added feature that it can also do true spherical geometry. And the UCL PDR code has been updated to do 3D geometry and is being used in hydrodynamic simulations. Okay, so I said that various emission lines are produced in different regions of the PDR, and these lines have different critical densities and different heights above ground, so they can be used to try to extract the physical conditions in the PDR. So this is an example showing multiple emission lines in which we tried to get the incident model UV radiation field and the model constant density. This could also be the model pressure if we have constant pressure models. And this is for RCW 49 using upgrade observations for a single pointing. And we get a UV field of about 10 to the 3 and a density of about 3 times 10 to the 3. And this is one of the plots that Mark will be showing you how to make. We can also get independently maps for the UV field and the density. These come from your line intensity maps. And this is an example from Knight and Peters et al. For the reflection nebula NGC 1333. And this used FIFI-LS data. Again, Mark's going to show you how to do that. Now, molecular hydrogen is also an important diagnostic in PDRs. This shows an energy level diagram for H2 as a function of distance between nuclei. So down here is the ground electronic state, and we have two excited electronic states. Then within each electronic state, there's vibrational levels and then rotational levels. So if you look at V equals 0, J equals 7, that's about 4,600 degrees above ground. So it's possible to excite that by collisions in a PDR. If you look at V equals 1, J equals 3, that's about 7,000 degrees above ground. That gets more difficult to excite in a PDR by collisions. But another way to excite lines, H2 lines, is by UV fluorescence. So a photon that's greater than 11.2 EVs can be absorbed up to these electronic levels. 10% of those pumps land in the vibrational continuum. So that's what breaks the molecule apart. But 90% of them land in bound states, which then cascade down through the rest of these levels. And so that can populate these upper levels. So the lower levels can be collisionally excited. The upper levels are probably UV pumped. And these intermediate levels, they might be UV pumped, they might be collisionally excited, depending on the densities and temperatures. But one way to sort these out is by making H2 excitation diagrams, which also Mark will show you how to do. This is a plot of the column density in a level, which you get directly from observations, divided by the statistical weight as a function of the energy of that level above ground. So the lower levels are collisions, the upper levels are UV pumped. If you plot a line through these lower levels, you get an estimate of the gas kinetic temperature. You can also get a temperature for these upper UV pumped transitions, but that's not really a gas kinetic temperature, but it does tell you something about the excitation of these levels. If you go down to 0 here, you can get an estimate of the column density in the cold gas and a column density in the of these upper UV pump levels. You can also get an estimate of the ortho to pair ratio by finding the factor which puts all these observations on the same line. I want to talk about H2 region diagnostics for just a minute. If you can get the electron density and the electron temperature, that gives you the thermal pressure, which is an important boundary condition for the PDR. And iron plus looks to be promising to do this with using JWST observations, because many of these transitions are within the JWST bands. So this is iron plus energy levels as a function of temperature above ground. And what transitions will be good diagnostics? Well, if you have this level, transitions that come from the same level, then they have the same dependence on temperature and density. So those are not good transitions to use. But if you look at levels that are just have a very small difference in temperature above ground, then those are good density diagnostics. If you look at levels that have wide differences in temperature above ground, then those are good temperature diagnostics. So we calculated volume emissivities from a slightly modified version of Chianti, and we plot these as ratio plots, which we call phase space plots. Mark also will show you how to do these. But this is a ratio of 1.64 over 5.34. So those have very different temperature dependencies. So that's a good temperature diagnostic. And this is 1.60 over 1.64. And they have nearly the same temperature dependence. So those are good density diagnostics. So the idea is you can plot your observations in this phase space plot and get an idea of the thermal pressure. Now I want to talk a little bit about caveats, things to watch out for when you're applying your models to observations. And first I'll start with geometry. Most of these PDR models are for face-on PDRs. Now, what I mean is that the source of illumination is perpendicular to the surface of the cloud, and your line of sight is along that line of illumination. So the emission that you see comes from the illuminated surface. But not all sources are face-on. Some sources are edge-on. And one example of that is the Orion bar. So here we have the trapezium way up here, which is illuminating this wall of gas. And we see this wall of gas that's edge-on. And so the PDR is spread across the sky. So what changes? The optically thin lines increase compared to the face-on PDR by a geometrical factor. So that factor is the column density along the line of sight compared to the column density that's face-on. So lines such as the H2 lines or 01, 145 micron line can increase by quite a bit due to this longer column density along the line of sight. Lines that are optically thick or marginally thick increase by a factor of a few. So the 63 micron line is thick, the carbon-2 line is marginally thick. You can only increase these by a factor of a few for edge-on PDRs. And then the intensities vary across the sky. There's not just one line intensity that's emitted directly face-on from the PDR. So here's an example we did in the Pabst et al. Papers. This is for an edge-on PDR. The source of illumination is off on the right. So this is an AV of 0. This upper panel here shows the temperature. So it's warmer at the outside, cooler in the middle. And then these are the emergent line intensities moving across the PDR, accounting for the optical depth effects. So we have carbon-2 in green, O1 is in purple. Here's the CO 2:1 line. Now this is a log scale. So really what you see are the peak line intensities here. You don't really see this much fainter stuff. But here CO 2:1 has this sort of broad continuum you see on an edge-on PDR. Another thing to watch out for are the effects of the metallicity and the grain properties. All PDR models make some assumptions about the metallicity and grain properties. Sometimes it's hard to know exactly what the assumptions are or even how to change them. So let's look at the extinction curves. So this is A lambda over V over wavelength or 1 over wavelength in microns. So this is the UV side. This is 1,000 angstroms. This is the infrared side. This is 1 micron. And these shows the extinction curves for the Milky Way here, dashed, and the SMC in purple. So the purple SMC extinction curve is quite high in the UV. Heating occurs at 6 EVs and higher. H2 dissociation occurs at 10 EVs and higher, and carbon photoionization is at about 11.2 EVs or higher. So these extinction curves really change where these processes occur. It changes the how far the UV photons can penetrate into the cloud. So a high extinction curve tends to collapse the layers of the PDR. On the other hand, there's the conversion to AV. So what is the column density that it takes to get an AV of 1? In the Milky Way, it's about 2 times 10 to the 21, but in the SMC, it's almost a factor of 10 higher. And this works in the opposite direction of the extinction curves. High extinction tends to collapse the layers of the PDR, but this large column density tends to expand the layers of the PDR. There's also the gas phase abundances, how much carbon and oxygen there is in the gas phase. And I should also mention the radiation field hardness. A hot star produces more UV and more dissociation, more heating. A cool star produces less UV, less dissociation, less heating. So some of the PDR codes, it's very easy to change these kinds of parameters. Not all of them, but some of the parameters, just from an input file. In other codes, it's quite difficult. You really have to dig into them to figure out how to change them. And they don't all change in the same direction. These parameters work in various different directions. And the last thing to watch out for that I wanted to mention is self-absorption. Lars talked about this as well. This is the S106 observations from GREAT. There's the carbon-2 line in red, and there's the O1 line that shows this self-absorption. But I think there's some misunderstanding about the self-absorption as far as the models go. The PDR models account for optically thick lines. They account for self-absorption, or if the line is absorbed or not, it's accounted for in a PDR model. Here's an example that I did for some time ago for CO in a GMC. And for these conditions, we found that the CO 1 to 0 line and 2 to 1 line could be quite self-absorbed. And that's because at the edge of the cloud, the levels become depopulated, and so the surface layers are absorbing the CO line, which is produced deeper into the cloud. So if the models account for the optically thick lines, then well, what's the problem? Well, the problem is that sometimes you see line ratios like 145 over 63 that's bigger than 0.1. And you just cannot produce a ratio that large from a single face-on PDR. So the idea is that the O1 63 micron line is absorbed in foreground gas. So that decreases the 63 micron line intensity and makes a large ratio. So how do you get that? Well, it's not entirely understood where this foreground gas is. But one way is, say you have your PDR and the 63 micron line is emitted from your PDR. There's some cold gas along the line of sight, and that absorbs out some of the 63 micron line emission and makes a self-absorbed profile. Another way to do it, though, within the same cloud is if you're looking at the other end, so the PDR is at one end, and within the same cloud, or outside the cloud at the other side, you're looking through this cold gas. Your line of sight could be over here, but it might also be up here towards the top, anywhere where you're looking through a colder column density within the same cloud to produce that self-absorption. Typically, it's found, at least so far with the limited number of observations, that an increase in the 63 micron line of about 2 to 4 is required to bring that 63 micron line back into agreement with models. So I am going to end it there. Let's see.
Thank you, Mark.
And take questions for a couple minutes before Mark gets started.
Lars has a question. Go ahead and unmute.
Hi, Mark. Very interesting talk. A very good summary of PDRs. I was wondering if you can comment a little bit on, so you mentioned, for example, the UCL 3D PDR model where they basically post-process hydrodynamical simulations. Is it basically what they get in the end, sort of combination of line of sight effects? So we have edge-on and face-on PDRs, or is there more complication that with respect to, for example, the slab layer models that are regularly?
So they you do get edge-on, face-on effects, but one of the biggest changes for hydrodynamic simulations is that there's various ways for the UV field to penetrate into the cloud. In a face-on slab model, it has to go through all the layers of gas. But in a hydrodynamic simulation, there's sort of voids and filaments. So there's other ways to illuminate the interior of the cloud. And that's sort of a classic example of that is the C1. The C1 line seems to be much more widespread than you'd expect for just kind of slab models. But the idea is that perhaps the UV radiation can penetrate into the cloud and dissociate some CO, and you get this more extensive C1 line emission.
Thank you very much, Mark. I'm not sure if I see another question. Otherwise, I wanted to actually ask a very quick question regarding the lower limit of the FUV field, so 6 electron volt. I was wondering where that actually comes from. Is it just because it sounds arbitrary?
Yeah, so it's kind of a historic number. I mean, we say 6 CVs because people have been using that for a long time. It's true though that you could get heating from lower energies. The 6 CVs originally came from the energy that's required to dislodge an electron within a PA and get it to the surface so that it can contribute to the heating. That's originally where 6 CVs comes from. But you can also get heating from photodetachment of electrons from PAs. That requires much less energy, maybe 3 EVs. And so it's true, you really can get heating from the lower energies, from even optical photons. But in these regions that we're talking about, the PDRs next to OB stars, most of the energy is in the higher energy bands and not the photons that would produce photodetachment of electrons.
Thank you very much, Mark.
We have a couple more minutes. Does anyone else have any other questions? You can raise your hand or put them in the chat. Maybe while people are thinking, I maybe have a quick question. So you talked about some of the things to watch out for, but I was wondering how much of an effect you would expect from the layers between like the ionization, dissociation, etc. The fact that they maybe are not like definitive layers, but there's mixing between all of those phases.
Yeah, so there's a JWST ERS project to observe the Orion bar, and so that is going to have fabulous resolution, and that's one of the things that's going to start to look at because they're not like really sharp edges. There is mixing between all those layers. So I think I'm going to wait to try to answer that and to see what the observations tell us.
Makes sense. Thank you.